Good morning, physics. It is Wednesday, May 6th. I hope you all enjoyed your breakfast of love. Today we're going to be talking about standing waves. Now, with standing waves, we talked, previously, yesterday, you should have read a bunch about how waves interact with each other and how they interfere in some ways, how they can be either constructive interference or destructive interference, as well as how they interact at boundaries, so places where your wave is fixed. So if you have something which can slide up and down, you're going to have pulses, incident pulse, which is the pulse you send, and then the reflected pulse, which is the pulse that gets sent back to you from a fixed end. And there's lots of ways to sort of show this and sort of how they all end up interacting with each other, how they sort of can either increase the size of a wave or decrease the size of a wave, or do that in various points, which is pretty interesting. But what we're going to be talking about today is a particular type of interaction called standing waves, which are very common in stringed instruments, as well as with pretty much actually all instruments, even your wind instruments. There's usually a standing wave created that causes the amplification of sound. And the way these standing waves sort of work is basically the idea here is you have a part of the wave, which is called the antinode. So the antinode, you have nodes, which are the parts that don't move, and you have antinodes, which are the parts that are constantly moving back and forth. So in this diagram, you have each of these orange dots is a node, and everything else would be antinodes. So this first wave in red has 2 nodes, 1 antinode. And then this one in orange, 3 nodes, 2 antinodes. And then this one, 4 nodes, 3 antinodes, 5 nodes, 4 antinodes, so on and so forth. Now, the reason why that's important, those are called harmonics. And so with those harmonics, they occur at certain frequencies or at certain wavelengths that sort of cause it to create these standing waves, because as you're sending one wave pulse down the line, another wave pulse is sort of interacting in a very specific way, and sort of like this perfect harmony, where it ends up causing one part to vibrate and other parts to stay non-mobile. So you end up having this amplification effect in one particular area, causing like harmonics, which is also one of the things where it sort of just keeps building and building on itself, and sort of allowing the vibrations to really flow through there. So with that, there are a couple videos I would like to show. One of them is just sort of looking at, recreating these standing waves. If you had something like, I have some of these coiled springs in the lab, which unfortunately we're not really going to get to use, but this is basically the idea of it, where you have you can send pulses and you can sort of see how that wave gets reflected and all of that. Like it showed in one of the first examples, and now we can create some harmonics. So this would be the first harmonic, as in we have 2 nodes, 1 antinode, and the harmonic series is based on the number of antinodes. Let me actually just speed this up a little bit. And then we have a second harmonic. So as you see, there's 2 antinodes going on. And then there's a node in the center, and then the 2 ends, which are mostly stationary. And then we get 3, which, as you know, you have to shake your hand back and forth a bit faster. With each harmonic, you're ending up adding more and more energy. As you can see, it's flipping back and forth pretty quickly. And so to reach these higher and higher harmonic frequencies, you need to add more and more energy. And a sort of cool way to sort of see that is sort of some physics applied to a guitar, as seen here. And as you can actually see the standing waves being formed. This person sort of synced up their camera pretty good to have a really high frame rate. And also just like time it, shutter speed set up right. So as you can see, like each of these strings, the lower ones, so the ones down below, are generally, so like these strings are higher frequency, so they were creating a higher pitch noise, and as you can sort of tell, their wavelengths are smaller. They were much closer together than those standing waves. And then for, let me turn this down a little bit more. And then for, say, these ones up higher, the wavelength is a little bit longer, so they're producing lower frequency notes. And so overall, that's just kind of a cool application of how these standing waves work. And hopefully, you can sort of use that idea of like how the size, the length, and sort of the amount of standing waves affect the sound. If you have sort of higher vibrations, you'll end up with shorter wavelengths and therefore a higher pitch. So like when you're playing a guitar, if you move down the neck, you end up playing higher and higher notes, and that's because you're shortening the length of your string, causing a only really higher, shorter wavelengths being able to be created, and therefore shorter harmonics, or higher harmonics where you have higher frequencies going on based on the length of the string. And so that's one of the key things of why violins, cellos, guitars, all those instruments sort of, when you play up, you have higher pitched notes on the neck. So hopefully I gave you enough information here to be able to answer these questions. It's one of those really cool things and something that I personally want you all to investigate. You know, spend some time doing a little bit more research on sort of how these standing waves and music, because a lot of people have exploited this in something that we're going to explore a little bit more on Friday, such as some of the videos of people, say, playing various covers using only melons that they turned into ocarinas, and sort of the ideas of how those work, or like things like using an electric toothbrush to play Take On Me by a-ha, and those ideas. So it's kind of cool and a very interesting application of these physics principles to create these sounds and like things that you can even program in and sort of make your own music. And it's just overall really cool, and one of my favorite things about sound and waves. So that'll do it for this video. If you have any questions, you know where to reach me, and have a good day.